This first video is going to set the stage and tell us a little bit about how computers generate random numbers and why that might be helpful. So what is Monte Carlo simulation? Well, it takes its name from a famous casino in Monte Carlo, and it refers to the use of a computer to repeatedly carry out some kind of random experiment. We're going to keep track of the outcomes, and then we're going to compute relative frequencies, maybe summarizing them and plotting them in some way. The point of all of this is that in a simulation, we know the ground truth. We know how the data were generated, and that means we know the values of any parameters that in real life we'd be using data to infer. This allows us to pretend that we don't know the truth, and then check how well estimators, confidence intervals, tests, and other statistical procedures actually perform in finite samples. Because we're only pretending we don't know the truth. In the simulation, we actually do know it, so we have a basis for comparison. We can also use Monte Carlo simulation to check probability calculations by simulation. Sometimes we can get an analytic result that's sufficiently complicated, we're not sure we've done it correctly, and a quick simulation can be very reassuring. Certainly, if the simulation does not agree with what you calculated by hand, you'd better go back and double check. We can also use Monte Carlo simulation to approximate probabilities that can't, in fact, be computed analytically. I'm going to tell you a little bit about how simulation works under the hood, but if you want to learn more, I've listed a few references here that you can click on. Again, if you visit the course website, detralia.com/erm, you'll find a copy of these slides in HTML format, and all these links will be clickable. The first question that we have to address is, what are we even talking about when we talk about carrying out a random experiment on a computer? It turns out that the question of what randomness is actually a very challenging philosophical problem, and it does not have a completely satisfactory solution. When we do a Monte Carlo simulation, we're going to be working with a frequency type definition of probability. In other words, we're going to be treating probability as the long-run relative frequency of events that would occur if you repeated something over and over forever. That is not the only interpretation of probability that's out there. It's going to work perfectly well for our purposes in a Monte Carlo simulation. If you're interested in this sort of thing, I would strongly recommend that you check out some of these references. I do think that sometimes when we do statistics and probability, we forget that some of the concepts that underlie our methods are of a relatively recent vintage. Rather, their intellectual heritage doesn't really go back that far. There's still lots of disagreement, in fact, about the foundations of statistics. And it can be interesting sometimes to stop and think about these things, even though for carrying out a simulation, we don't necessarily need to worry too much about the distinctions. The first thing you need to know about random numbers generated on a computer is that they are not, in fact, random. Computers are totally deterministic. If you put in the same input, you're going to get the same output. So in fact, what are called random draws on a computer are not in fact random, they're pseudo-random, which means as if random. So while they are generated by a deterministic algorithm, they are generated in such a way that they appear to be random. What we mean precisely when we say this is that they would be indistinguishable from real random numbers using statistical tests. So these pseudo-random draws are perhaps better called statistically random. For our purposes, it turns out that pseudo-random is actually good enough. And to avoid really wasting space on the slides and having trouble pronouncing things, I'm just going to write RNG below for pseudo-random number generation. But it is important to remember that, in fact, these draws really are not random. I could not resist providing this famous quote about using arithmetical methods of producing random digits. That is, about generating pseudo-random values on a computer. Now, if we're going to be in a state of sin, then it's at least a bit comforting to know that R's method for generating pseudo-random draws involves a 16th century cleric. The method is called the Mersenne twister, and it's based on some concepts from number theory that were developed by Mersenne. It has nothing to do with the well-known game twister, but the game twister at least tempts us down the path of sin, so it's good to know that we've got a cleric on hand to take our confession if necessary. Okay, joking aside, there is an algorithm that's called the Mersenne twister, and it's quite complicated. This is how R generates its pseudo-random draws. I'm not going to show you how this algorithm works, but I want to give you a flavor of what's involved when R is making pseudo-random draws. So I'm going to show you on the next slide a much simpler pseudo-random number generator called the Lamer RNG. The basic idea here is we need some way to make uniform draws. And if we've got those, then we're going to be able to find a way to transform them into draws from some desired probability distribution. So I'm going to start off by showing you the first step, how to get uniform draws, and then we'll talk about the second step. Now, in real life, you're not going to implement this part yourself. You're going to rely upon R, but it's good for you at least one time in your life to see the details so that you have a little bit of an appreciation for what's going on under the hood. Okay, so here's a very simple pseudo-random number generator. This is how it works. Step 1, choose integers m and a, where m is strictly positive, and a is also strictly positive and less than m. Again, both of these are integers. After choosing the two parameters m and a, you're going to choose another value called the seed. I'll call that x0. The seed is going to be the starting value for our pseudo-random number generator. And the seed needs to be positive and less than m. Now we're ready to actually construct our pseudo-random draws. So to construct our sequence xn, we're going to set the next value of x equal to a times the current value mod m. So what does that mean? That means the next value of x, so xn plus 1, is the remainder when a times xn is divided by m. We can run this for a long time. We'll get a whole sequence of xn values. And finally, to obtain our pseudo-random uniform draws, what we're going to do is simply rescale the x's. So we'll divide them all by the same number, m. When we're done, the values x1, x2, x3, all the way up to whenever we stopped, will be approximately uniform 0, 1. I say approximately. They're not going to be exactly uniform 0, 1. And I should also point out that the choice of m and a really does matter. So it's possible to choose lousy values of m and a, which will give you a terrible sequence that does not do a good job of approximating uniform draws. So it's important to make good choices here. The choice of the seed does not affect the quality of the output. It is merely the starting value that you need to run the program. Again, the point I'm trying to drive home here is xn is a completely deterministic sequence. And that means that the pseudo-random draws xn over m are themselves completely deterministic. If you choose the same seed as I do, and the same values of m and a, you are going to get exactly the same draws. So let me show you a little example now. I'm going to need to choose some parameters m and a. These are not the best choices in the world, but they'll work for the purposes of illustration. So I've set m, which remember needs to be a positive integer, to 2 to the 16th plus 1. That is 65,537. And I have set a, which needs to be a positive integer between 0 and m, to 75. Just for fun, I'm going to take the seed, which needs to be between 0 and m, equal to the year in which I was born. And then I'm going to begin the iteration. So first, I will construct x1. To do this, I'm going to need to use an operator in R that we haven't looked at yet in the course. This is %%. So if you enter x, %y in R, then R will return the remainder when x is divided by y. And that's exactly what we want here. So I'll set x1 in line 9 of the first code block equal to a times x0 %%m. So x1 is the remainder when a times x0 is divided by m. Let's take a look at the value of x1. Okay, it's 17,651. Now we're going to continue the process, setting x2 to be a times x1 mod m, x3 to be a times x2 mod m, and so on. So I'm just going to make a sequence of length 5. Then I'm going to throw away the seed, and I'm going to look at the values x1 through x5 divided by m. And these are supposedly pseudo-random uniform draws. Well, they don't look too bad. They're certainly between 0 and 1, and they appear to be sort of roughly uniform. On the problem set, you're going to expand upon and improve this example, and you'll also look at some related some related work that is going to turn these uniform random values into other things that you might want, like normal random values. As I said a moment ago, we're not actually going to roll our own uniform random variables in R. When we want to generate random values in R, we're going to use built-in functions. Here's the simplest one. It's called sample, and you can use it to make draws from some vector in R. The syntax of this function is sample x, size, replace prob. I'm going to go through each of those arguments in turn. So this generates a random sample of length size from the vector x. So you supply some vector x. But if you don't want to supply a vector x, you can also just supply a positive integer. In that case, R is going to construct the vector for you. The samples will be drawn from the vector 1 to x. Now, by default, these draws are made without replacement. If you want to make them with replacement, you need to set the argument replace equal to true. Also by default, the elements of x are going to be sampled with equal probability. If you want to sample them with different probabilities, that's fine. It's easy to change. Just supply the argument prob and create a vector of probabilities that corresponds to your vector x. Here are some simple examples. In the first code block, I'm going to draw without replacement from a vector red, blue, green. This is a character vector, and I'm using it to represent a bowl with 3 marbles, 1 red, 1 blue, and 1 green. Here's how I can take a sample of size 2 from these marbles. All I have to do is sample marbles size equals 2. That will draw 2 marbles without replacement. My second example is sample 10, comma, size equals 5. This makes 5 draws without replacement from the vector 1 to 10. So we can see that in each of the first 2 examples, there are no repeats. And the reason there are no repeats is we never replace elements of x after drawing them. Once you take them out, they're gone. Now, as everyone knows, Core ERM is the best course in the world, so I've written a little message to that effect here in the form of a character vector. I'm now going to sample with replacement from this vector of 3 strings. Notice I'm getting repeats, and that's because I've set replace equal to true. Finally, in the fourth code block, I'm going to give you an example of drawing with unequal probabilities. What I want to do is draw true and false, where false has a probability 0.7 of being drawn. To do that, I just need to specify a vector prob that has the same length as my vector x, and that has probabilities corresponding to the elements of x. So as you can see here, I've made 20 draws with replacement, where false has probability 0.7, true has probability 0.3, and it does look like I'm getting more falses than true, as I should. Now, if you run this code, you are probably going to get different results from me because it's random, or at least it's pseudo-random. If you want to make sure you get exactly the same draws as me, however, you can do that. What you need to do is set the seed. Remember a few slides back when we rolled our own uniform random number generator, we needed to supply this initial condition x0 called the seed. RNG is deterministic. The same seed gives the same draws. And in R, we can set the seed by using the command set.seed, and then you specify the seed that you want. Your seed should be a single numeric value, and it will be interpreted as an integer. So if I want to set the seed again to my year of birth, I can do that. Let me sample from the vector 1 to 100. I'll make true draws without replacement. OK, I got 67 and 18. If I use that command again in the second code block, I'm probably not going to get the same values. It's pseudo-random. But if I set the seed back to 1983, as I do in the third code block, I now get exactly the same draws again. Now you may wonder, why would I want to set the seed? Why would I want to get the same random draws? Well, the answer is that we like our work to be replicable. If I carry out a simulation study and I send you the code, I want you to be able to run it and check the results that I got against the ones that you got. The only way I can do that is if I ensure you get the same pseudo-random draws as I used. Setting the seed ensures that. So if you set the seed and you rerun your own simulation experiment, you'll get the same results. Or if someone else reruns your simulation experiment, they will get the same result. One question I've gotten in past years is, well, should I be resetting the seed every time I make a random draw? Now, the answer to that is definitely not. So think about what would happen if you reset the seed after every draw. Then you'd be resetting the initial condition of the pseudo-random number generator to the same place, and since it's completely deterministic, that means it's just going to spit out exactly the same random value. If you did this after every draw in your simulation, you wouldn't have a whole sequence of different draws. You just have the same draw again and again and again and again and again. So I'm not saying to reset the seed after every time you make a random draw. What I'm saying is if you're carrying out a project or a simulation study, at the very beginning of the study, set the seed, then run everything down to the end. The next time that you run the entire program, you're setting the same seed, you'll get the same sequence of random draws from start to finish. If you want to obtain truly random values, this is actually possible. The way you could do it is you could supply a truly random seed. Your computer isn't capable of giving you one, but you could visit the website random.org, and they will provide you with custom random seeds to your heart's content. We've now reached the end of this video, so it's time for some exercises. The first two exercises ask you to think a little bit more about the function sample. And the third exercise asks you to write a function. This function is called rburn, that stands for random Bernoulli. And I'd like you to use the built-in R function sample to construct your function rburn. We'd like rburn to make a sequence of n independent and identically distributed Bernoulli p draws. The arguments of this function should be n, the number of draws, and p, the probability of success. Success, remember, in a Bernoulli experiment is a 1. So this function should return a vector of length n that contains only zeros and ones. You can check your results by making a large number of draws and then verifying that the fraction of ones is indeed approximately p.